In this section, we'll learn about some simple plotting tools for exploratory data analysis. Now, you might ask, what is exploratory data analysis? Exploratory data analysis is a task of analyzing our data using simple tools from statistics, from simple plotting tools, from linear algebra, and other techniques so as to understand what our data set is before we go and model and do actual machine learning. But this is extremely important stage. For any given problem, the first thing that we do is actually exploratory data analysis. This is like, it's called exploratory because we don't know anything about the data set when we start. We are trying to understand what the data set is about by being a Sherlock Holmes. Okay, so that's what this exploration is all about. It's about understanding what the data is. In this section, what we will do is we will try to understand this data. We'll try to understand some basic plotting techniques using a sample data set. The data set that we will use, so this is a very simple, very basic toy data set. Actually, it's a real world data set, but I call it toy because it's so simple. It's used in most textbooks, in most courses to introduce the basic concepts because it's very easy to understand. You can think of it as sort of like the hello world of data science, right? Hello world of data science. Actually, when you learn any new programming language, you write a simple program to print hello world. This is the equivalent of it. If you want to think of it like that, if that helps. And let's understand this data set. And we'll also introduce some terminology which will help us. So this whole document is an IPython notebook, as you would have realized by now, and I provide all the links that are useful to understand this. So first is a Wikipedia link. I will use Wikipedia extensively, as I told you earlier, during this course because it's easy, it's exhaustive, it has great references. And let's go to the iris flood dataset. Now, when I go to the Wikipedia page and when I go to the dataset place, I see this data. So a dataset is nothing but a table, if you want to think about it bluntly. Now, let me introduce you to what this dataset is, what problem we are solving, and a bunch of terminology. Now, in 1936, this dataset was collected from 3 types of flowers, all belonging to the iris family. The first flower is called Iris setosa. The second type of flower is called Iris versicolor. The third one is called Iris virginica. All 3 of them belong to the iris family. Now, so if you look at it, these 3 flowers look more or less similar, right? So the task that we have, the objective that we have, as I've clearly mentioned here, the objective that we have is to classify a flower as belonging to one of the 3 classes, right? So given a new flower, our task here, which is very important, when we're doing data analysis, we need to always keep in mind what our task at hand is, because that determines what type of analysis, what type of plotting we would do. So let's understand our objective here. Our objective is, given a new flower, let's assume there is a garden. The garden has 3 types of flowers, Iris setosa, versicolor, and virginica. Now, if a person picks up a flower and brings it to us, can we determine whether that flower belongs to the setosa class or the virginica class or the versicolor class? So we are doing something like a classification task, right? So if you want to think about it, what we're doing is a classification task. So our objective is to classify a given flower into one of the 3 categories. Right? Let's be very, very clear about the objective, because as I've just told you a little while earlier, it is important that we do our data analysis in line with our objective. Now, given these 3 flowers, if you look at them visually, they look very similar. Now, what we could do is, okay, given this task to us, we could go to a botanist who studies plants or a biologist broadly, and we could say, how do you determine, how does a biologist or a botanist determine whether a given flower is setosa, versicolor, or virginica? And a botanist could say, okay, I measure these 4 variables. I measure things called sepal length, sepal width, petal length, and petal width. And based on these 4 numbers, I know whether it is setosa, versicolor, or virginica. Now, the task that we're trying to do is we are trying to mimic an algorithm, a machine learning algorithm, to do what the botanist knows, what the botanist has learned by studying biology of these plants, right? Now, given that, now you might ask, what is sepal and what is petal? Let's understand that. So here is a very nice diagram of what petal and sepal are. So given this flower structure, you have this larger component called a sepal. The smaller one is called a petal. Now a sepal length is nothing but the length of this sepal. Let me draw a straight line here. And the sepal width is nothing but this width. Similarly, petal length is the straight line, is the length of the straight line in centimeters, and petal width is this component, right? So these are the four features. So when a botanist is given a new flower, he would actually look at these four values and they would say whether it is virginica, versicolor, or setosa. Now, since the biologist uses these four variables or these four measurements, it's possible that we could use these four measurements and build a simple algorithm which can classify a given new flower into setosa, virginica, and versicolor. As I've told you earlier, machine learning is all about learning from data, right? So let's see, in 1936, before the advent of modern computing, this data set was collected. And in this data set, you have, so the data set is nothing but this table. If you want to think about it, this table basically has four fields. We can call them fields or variables. So let's call these things variables. So you have four variables here, right? And each of these rows can be called as a data point or an observation. Again, the same thing could have multiple terms in machine learning because some of these concepts were discovered or were detailed by people from various departments. For example, the statisticians might call these four what we are calling as variables. The statisticians would call them as independent variables, right? A data point could be, for a mathematician, it's a vector, right? So since machine learning is at the intersection of many fields, from biology to computer science and mathematics, statistics, etc., the same thing might have multiple terms, and it's okay. I mean, we'll get to know these terms. We'll keep using them interchangeably over the duration of this course. Now, what we have to predict is this label. This is also called as a class label. So this is what we need to predict given these four measurements. So these four measurements are called variables. This is called a data point or a vector. And what we have to predict is called a class label. So just let's go and look at various terms that are typically used. So if you go up, what we have here is, it can be called a data point or a vector or an observation. So you might ask me, a vector is something that I learned in physics in my 12th grade. So how is that vector related to this? For this discussion, we can just think of a vector as nothing but n-dimensional numerical array. That's the simplest way to think of it for now, right? So you can think of it as an n-dimensional numerical array. So we have four variables here, right? So our data set is nothing but the whole table that we are given. Our features are nothing but your sepal length, sepal width, your petal length, and petal width, right? They're also called as variables or input variables or dependent variables. Your class label, which is the species of the plant, of the flower that it belongs to, can be called as a label or an independent variable, or it's called a dependent variable. I'm sorry, there's a typo here. This is called an independent variable, and it can also be called as an output variable or a class label, response label. There are tons of names for it, right? And going back to our vector, of course, we'll understand vectors in more mathematical detail when we learn linear algebra. But for now, you can think of a vector as an n-dimensional array. So going back to our example here, you can think of this as, a four-dimensional array, right? So you can think of this as an array which has four components or four dimensions, right? So this is what a vector is for now. For now, we can just think of it. This is a four-dimensional array. So if you just had an array which is 5.1, 2.1, let's say, this is called a two-dimensional array, right? So an array or a two-dimensional vector. So for now, just think of vectors as nothing but n-dimensional arrays, just for simplicity. There is more rigorous mathematical definition with all the properties of vectors that we will learn when we learn linear algebra. I promise you that. Now, going back to our task, since we understood some basic terminology on what is what, there's a very basic question. What is a one-dimensional vector, right? What if you have a vector which has only one component or one dimension? That's nothing but a scalar, right? From your physics, you might remember that scalars and vectors are different, right? So a one-dimensional vector is nothing but a scalar, if you want to think about it simply. Because instead of writing it like this, you could just write it as Instead of writing x equals to a vector of size 1 with only one value, which is 5.1, you could just say x equals to 5.1, and that would suffice. Okay, so going back to a data set. So this data set, now the first question I have, let's go question by question, because we are being Sherlock Holmes here, trying to understand what this data set is all about, right? So let's go and understand. So our objective is very, very clear, right? That's very important. You might ask me, why aren't we using color as a feature? Why are we using these four sepal and petal, which I don't understand? Why are we not using other very simple things like shape, size, or actually size is same as sepal lengths and petal widths? Why not? Why don't we use shape? Why don't we use color? So it's here in this case, the biologist or the botanist in this specific case knows what features are important. So domain knowledge is extremely important in machine learning. So machine learning is not just about crunching numbers, it's about making sense of the world. It's a very, very scientific process. So if you don't know what sepal and petal are, you'll never be able to make sense of what uh, make sense of what your solution is, right? So while machine learning has a lot of math to learn, a lot of interesting math to learn, it's also about understanding the domain knowledge. Imagine if these four fields or four variables were not given to you, what would you use? I would say, I don't know anything about plants. So let's go to a botanist and ask him. So please remember that it's extremely important that you have domain knowledge or you consult somebody who has domain knowledge to understand what's happening, to solve a problem much better than somebody who is just doing number crunching. Machine learning is not just number crunching, it's about getting insights into data. That's a very, very important task that we have to do. So let's go and run. So my first question is, in this iris dataset, how many data points are there, right? So let's go through some simple code. Let's be the Sherlock Holmes. Okay, so I'm just importing a bunch of libraries. In our Python section, we learned about pandas, seaborn, matplotlib, and numpy. I'm just importing these libraries, and I've downloaded my dataset of iris.csv, which is a comma separated value file from this GitHub resource. And all that I'm doing here, as you have seen in pandas, is I'm just reading a CSV file. Remember, in machine learning, in exploratory data analysis, the amount of code that you have to write is much, much less than standard software engineering jobs. Because what is important in machine learning is not necessarily a lot of code. What is important is the richness of your analysis. Analysis is more important than code if I have to pick one of them. I'm not saying code is not important. You have to know basic programming, but you don't have to write hundreds of thousands of lines of code. Typically, we write tens of lines of code. I've seldom written code which is more than 100 lines to solve a task. Okay, so from this, so I've just read my file, and now my first question is how many data points and features are there. So I could just use this simple function called print iris.shape. What iris.shape will give me is it will give me the shape of the matrix or the data table. So what this says is that I have a table which is 150 rows and 5 columns, right? So I have 150 rows and I have 5 columns, 2, 3, 4, so on and so forth. So it says that the table that I have, the iris.csv file, when I read it into my pandas object, what I get is basically 150 rows and 5 columns. My next immediate question is, what are the 5 columns, right? So you could just say print iris.columns, and what you would get is that the first feature or the first column is sepal length. So in your table, your first column is sepal length, your second column is sepal width, your third column is petal length, your fourth column is petal width, and your fifth column is species. Remember, species is what we have to predict. This is the output label, or this is the response label, or this is the class label that I have to predict. And these 4 are my features or variables, right? So this is how my table is, right? And I have 150 rows. Now my next question is, since I have 3 classes, I know this because that's what the dataset has. The dataset has Setosa, versicolor, and Virginica. I want to understand how many points are there which belong to the Setosa class, how many points belong to the versicolor class, and how many points belong to the Virginica class. For that, all you have to do is very simple. It's very, very straightforward. You just say iris species, you're taking the species column, and you're doing value counts. What it does is it gives you an output like this. What it says is there are 50 data points of the 150 data points that we saw a little earlier. 50 of them belong to Setosa class, 50 of them belong to Virginica, 50 of them become versicolor. Such a data set where you have almost equal number of data points for each of your classes is called a balanced data set. Now you might ask, okay, where do we find imbalanced data sets? Let's take a simple example here. Imagine if you're a data scientist working at a hospital, and let's assume the hospital has 10,000 patients, right? For each patient, you have many fields. Let's assume you have field 1, field 2, so on and so forth, field 10. So for each patient, each of these fields could be results of medical tests, it could be medical examinations, it could be doctor prescriptions, it could be a lot of features. Let's assume, instead of naming what these features are, let's just assume I have 10 features for each of my patient, right? So my data matrix will look like this. I have 10 features and I have 10K patients, each patient represented by a row here, right? Now, for each patient, I have a response or a class label which says whether this patient has diabetes or not. Of course, as you would imagine, only a very small set of patients that visit a hospital would have diabetes. So let's assume there are 500 patients out of my 10,000 who have diabetes and 9,500 of them who do not have diabetes. So they are non-diabetic. Okay. Now your task is, given these 10 features which correspond to some medical tests, you have to predict whether the patient has diabetes or not. Now here, if you notice, you have a data set with 500 data points of one label, of one class label, which is diabetes, and 9,500 of the other label, which is non-diabetic. Now this is called an imbalanced data set. This is called an imbalanced data set because you have two class labels and the number of data points per class label are very different. Now you might ask, what if instead of having 500 and 9,500, what if I had 4,000 patients who are diabetic and 6,000 patients who are non-diabetic? If this was the case, would you call it an imbalanced data set? I would say this is almost balanced because it's not as severely imbalanced as 500 and 9,500, right? So this is okay. The reason we are specifically calling out imbalanced data sets is because when you have an imbalanced data set, we have to do slightly different data analysis as compared to a balanced data set. Slightly different, not significantly different, but slightly different. And it's important to understand whether your data set is balanced or not. In our case, thankfully, for the IRIS data set, it's a very balanced data set. Now let's go and understand some very interesting, simple plotting tools, right? So let's do something called a 2D scatter plot. Okay, so the code of it is very straightforward. So you just say iris.plot, you're doing a scatter plot, so you're saying the kind equals to scatter, and on your x-axis, you're saying plot sepal length, on your y-axis, plot sepal width, right? So, and you just say plot.show, which will shows the plot that we are plotting. Now, always remember, whenever you see a plot, always look at what the x-axis is, what the y-axis is, what the scale is. In this plot, this is not 0, 0. This is not 0, 0. That's very important to remember, right? Because this is starting at 2, this is starting at 4.5. So always look at your axis and read the scale. This is called the scale of a plot. Always read the scale, always read the legend on what these axes are. This axis is sepal length, this axis is sepal width. And for each point, what we've done is, we have 150 points in our table, right? We have 150 points in our table, and we had sepal length, sepal width, petal length, and petal width, right? And we also had the species, whether it belongs to Setosa, versicolor, or virginica. Now what we've done is we have taken sepal length and sepal width. So for each flower, I take, let's assume the sepal length is 5.5 and the sepal width is 2.1, right? Then I would say, take the sepal length as 5.5 and take the sepal width as 2.1 and put a point here. That's how I plot my scatter plot. It is called a scatter plot because we're scattering all of these points that we have and putting it on a map. So it's a simple scatter plot. Now you might ask, okay, we are doing a scatter plot of only 2 dimensions. What about 3 dimensions? What about 4 dimensions? What about 100 dimensions? Well, in physics, you might have heard about the 4th dimension as time. In machine learning, 100 dimensions is not unheard of. It's very commonly found. Imagine if I have 100 features, I'm operating in a 100 dimension space. So let's not worry about 100 dimensions or 1,000 dimensions, what they mean. Think about each dimension as a feature or a variable that you're interested in to solve your problem. Okay, so now the big problem in this is I don't know where is setosa flowers, where are versicolor flowers, where are virginica flowers. This is just a map. All that it tells me is your sepal lengths typically vary between 4 to 8, right? Your sepal length typically varies from 4 to 8. Your sepal width typically varies from around 2 to 4.5. That's all it tells me. It doesn't tell me anything else. So what we can do here is we can color these points based on what class they belong to. So let's go to that quickly. Here we'll use, so SNS here corresponds to, if you look at how we imported these libraries, SNS is nothing but your Seaborn. Okay, so Seaborn gives us very nice tools to plot this thing. So let's go through the code. It's very, very simple. So all that I'm saying here is set a white grid, which basically gives me this grid structure for my plot here. And all I'm saying is here is color them. The hue parameter here says by which column in my data set should I color these points. So hue equals to species basically means color these points based on what species value they have, and plot a scatter plot here with sepal length on x-axis and sepal width on y-axis, and add a legend. We'll see what legends are. Legends are very, very important. So for a data set, typically this is what is called a legend. For a plot, this is a legend which says what color is what class label. This is called a legend. This is your x-axis label. This is your y-axis label. This is the scale of your plot. Now, as soon as you see this, you see that all of your setosas are blue in color here. All of your versicolors are in orange in color here. And all of your virginicas are green in color. Now, the first immediate takeaway, and what is the x-axis here? Sepal length. The y-axis here is sepal width. The first important takeaway, let's never forget our objective. What was our objective? Our objective was, given a new flower, to distinguish whether it is setosa, versicolor, or virginica. Right? So we had a classification problem. Now by looking at it, can you do something? So the first observation I have here is, this is a 2D plane, right? Your x-axis is sepal length, your y-axis is sepal width. And now you see that all your blue points are well separated from your orange and green points, right? But your orange and green points are not well separated. Now imagine, just imagine that if I can draw a line here, I'll just change the color here. Let's assume I draw a line here, okay? And I say that everything on this side of the line is setosa. See, we know how to draw lines, right? What if I draw a line? A line in 2D space, we learned it in our coordinate geometry in school. A line can be written as y equals to mx plus c. We learn more mathematical details as we go, but drawing lines is a very, very simple task, which is fundamental in machine learning. So here in a 2D space, we're drawing a line, and what if I can say that all the points on this side of the line belong to setosa, and all the points that are on this side belong to either versicolor or virginica, and I'm not able to determine. If I draw a line like this, what happens is I have this point which is misclassified as not setosa, right? So from this, what I can say here is, okay, by just drawing a line is nothing but a linear surface, okay? By drawing a line, I can separate my setosa points from my virginica and versicolor points. But can you draw a line to separate your versicolor? If I draw a line like this to separate my virginica and versicolor, it's not going to work, because if I draw a line like this, there are a lot of orange points on this side and there are a fair number of green points on this side. So the observation or the takeaway from this plot is that sepal length and sepal width features can distinguish setosa flowers from others if I can draw a line. So if you can draw a line and classify, that's called linearly separable. Right? It's a very simple terminology. So why is it called linearly separable? It's called linearly separable because so line is basically is also called a linear surface. We learn the mathematics when we learn linear algebra, but if I can draw a line here and say everything on this side, by drawing a line, if I can separate one class from other classes, that is great. That's called linear separability. But I can't linearly separate my versicolor and virginica flowers using these two features. Probably I can do it with other features. I don't know. Right now I'm just plotting it with sepal length and sepal width. Now, the immediate question I have here is, this is called a 2D scatter plot. A 2D scatter plot is basically you're drawing a two-dimensional surface where you're putting one point for each of your observations. And if you color it by the class label, you get a very good sense of what's happening. Now, the immediate question is, why can't I draw 3D scatter plots? Of course you can. Nobody is stopping you. So let's go and see how to draw a 3D scatter plot.